Hello everyone, I'm Satyajit Pattnaik and welcome back to my channel. I have started this small series on dimensionality reduction in machine learning, but in this video we will be focusing more on understanding PCA, principal component analysis, and in our next videos we shall be talking about the other algorithms such as LDA, QDA, Kernel-PCA, etc. So stay tuned. If you're new to the channel, please subscribe and hit the bell icon to get notified on my future videos. So let's get started. So as I told, today's topic is all about dimensionality reduction. We'll get started with that. We'll try to understand what exactly dimensionality reduction means, what exactly dimensions means, what are features and all those things on a very high level. But yeah, we will quickly jump into our main topics, which is going to be PCA for now. But yeah, this is going to be the agenda for this entire series. After PCA, I'll also be sharing videos on LDA. We will also be sharing videos on QDA and then kernel PCA. And also I will talk about the basic differences between PCA, LDA, and in real world scenarios, which one to use in which cases. And also after all these topics are done, I will also showcase you one of the real life example or a real life use case which is being used in one of the industries, and I'll show you how to use PCA, how to use LDA, and how to get our things done. Okay, so let's quickly get started. This is going to be a very overall concept. I will try to focus on each one of them slowly. So dimensionality reduction is mainly divided into two different steps. I hope that I know that there are a lot of articles on the web. Many articles say that PCA is a part of feature selection and vice versa. Some says PCA is a part of feature extraction. So don't get confused by these jargon words and all those things. Just try to understand the concepts which I'm trying to explain. Maybe you will have a very better understanding after my video is done. So dimensionality reduction is basically divided into two different steps. One is feature selection and one is feature extraction. However, the meaning of both of them are almost similar, so don't get confused by it. In feature selection, I call wrapper methods or some filtering methods or embedded methods as part of feature selection. Now what is wrapper method? Wrapper method is nothing but recursive feature elimination. Many of you who have already gone through linear regressions and all those things, we know how to do our recursive feature elimination, right? So wrapper method is something like that, where you have 10 features. Now when I say features, that means dimensions or my x variables. Okay, or you can call it as independent variables. So I have, let's say, 10 different variables, and I know that I have done some analysis. I have done some bivariate analysis, multivariate analysis, and got to know that this feature is not important. For example, gender is not important for churn analysis. So what I can do is I can simply remove that and see how my model behaves. Is the accuracy deteriorating? Is the accuracy getting better? And accordingly I will take my decisions. So recursively you are eliminating some of the features. Okay, that's kind of a manual process as well. Now the second technique is filtering methods. Now inside filtering methods there are concepts like information gain, chi-square, correlation coefficient. So these are some of the filtering techniques by which you can also do feature selection. And there are some embedded methods as well, decision trees. Apart from that, we also have random forest. Random forest, internally you don't have to perform any feature selection or feature extraction steps as a separate step, because internally when you call random forest, it gives you an intuition, it gives you an idea which all features are going to be important, and that's where you can take your problem statements ahead. Okay, so let's jump on to the feature extraction part. Feature extraction majorly has these four algorithms, but we do have some other algorithms as well. I will briefly talk about them at the very end of this particular series, but let's just quickly start with the basics. Okay, so very first we will be discussing about principal component analysis. Then we will be discussing about LDA, QDA, and kernel PCA. So let's not waste much time and let's quickly jump into PCA and let's try to understand what PCA means. Now in this video, I will be focusing on explaining you the theoretical part, as per my knowledge. But our next session will also be on PCA, which will be more on the mathematical part, how to solve PCA, how to get eigenvalues, eigenvectors using mathematics or statistics. Okay, so PCA is basically a dimensionality reduction algorithm, but it can also be useful as a tool for visualization, noise filtering, feature extraction and engineering, and much more. Okay, now why do we use PCA? The basic concept is clear. We use PCA for dimensionality reduction. That means in case we have more than 150 features or 100 features, and manually doing EDA is definitely not going to help, because there are like 100 plus features. So it's going to be very difficult to analyze each one of them manually. So in those kind of scenarios, you take help of PCA. So what PCA does is it converts your data, it converts your n number of variables or n dimension space to n PC components. I'll talk about PC components as well. Now, PC components is nothing but principal components. We'll talk about that. So the basic concept is clear. We were working on a dimensionality reduction algorithm problem to get rid of overfitting. Okay. Now the code part is going to be super simple, but let's try to understand how PCA works. Let me take help of paintbrush, or I usually go for paintbrush teaching. So let's take this particular example. Let me draw down some. Let's say I have variable 1, variable 2, variable 3, and variable 4, and I have sample 1, sample 2, sample 3, sample 4, sample 5, sample 6. Now variables are nothing but my x variables, right? My independent variables. Samples are nothing but how many records do we have. So here we are having 6 records. So let me provide some random values: 10, 11, 8, 3, 2, 1, 6, 4, 5, 3, 2.8, 1, and some random values. Okay. Okay, so right now I have this particular table. I have 4 variables, that means x1, x2, x3, x4, and I have 6 samples. Okay, that means I have 6 records. So obviously, if I have to plot this particular record in a 4-dimension space, it's not going to be possible, right? So let's talk about the 1-dimension space first, and then we will jump on to the multi-dimension space. Okay, now let's say I just have one variable. Just consider v1. I don't have v2, v3, and v4. So I just have one x variable. Now the data is 10, 11, 8, 3, 2, 1. Now if I try to project this value in a one-dimension space, it's going to be very easy, right? Let's say I have numbers from 0 till 15. So where will my sample 1 lie? Somewhere around here. Sample 2 somewhere around here. Sample 3 somewhere around here. Sample 4 somewhere around here. Sample 5 somewhere around here, and sample 6 somewhere around here. Quite easy. It's very easy to visualize in a 1-dimension graph, right? Now let's jump onto the 2 dimensions graph. Okay, v1 and v2. So what I will do is I will draw my x and y axis. So let's say this is my v1 axis and this is my v2 axis. Okay. Now let's say I have 1, 2, I have scales from 1, 2, 3, 4 till let's say 10. Here I have 1, 2, 3, 4, 5, 6, 7, etc, etc. Okay, so let's try to plot this. 10 and 6, 10 and 6 somewhere around here, 11 and 4 somewhere around here, 8 and 5, 8 and 5 somewhere around here, 3 and 3, simple, 2 and 3 here, 1 and 1 here, right? Quite easy to visualize and easy to perform our steps, and using 2 variables we are able to visualize it, right, very confidently, and it's quite easy for us. Now what about 3 dimensions, or we can say if we have 3 variables, v1, v2 and v3, it is still possible to visualize. Just consider I have v1 and V2 here, and V3 is an axis towards you. If you're working on your computer screen right now, or if you're watching the video right now on your mobile, just consider the Z axis towards you. That's going to be your V3. It is still possible to visualize, but what if we have variables more than 3? Is it possible to visualize in 4 dimension space or 5 dimension space? It's not possible. It's irrelevant, right? Because it cannot be plotted. We cannot plot graph on 4 dimensions, right? So that is the reason we have a concept of PCA. Now how PCA comes as a I would say how PCA comes into this picture, how PCA can take 4 or more variable measurements and make a 2 dimensions PCA plot. Now the concept is quite clear. When we are dealing with n variables, let's say here I have 4 variables. That means I have 4x variables, x1, x2, x3 and x4. Let's say I have 5 variables. Okay, x5. Now obviously I cannot plot it and see, right? I cannot do that. That's against the policies of nature, right? So it's against nature. It's just not possible. Now what PCA does is it converts the data into n dimension space to n PC components. Now what does that mean? If I have five different variables, it converts them into 5 principal components. Out of these 5 principal components, you can select the top 2 or top 3. Okay, I'm just talking about an example. Let's say I have 5 dimensions, I have 5 variables. Here, 5 variables, if you go through a PC algorithm, it will convert it into 5 PC components. That means PC1, PC2, PC3, PC4 and PC5. Out of them, definitely, let's say PC2 is the, so it's up based on your priority or based on your importance. PC2 comes first, PC3, PC4, PC1, PC5, something like that. So PC2 is the highest priority or the value is higher. PC3 is second highest, PC4 is third highest. Now, as an user, if I just want to consider 2 variables, I can simply consider PC2 and PC3 and take my problem statement ahead. So it will be easier for me to visualize, easier for me to understand as well. Now let's try to take a small example. Again, one more example and try to find the PC components. And then only maybe some of your doubts will be clear. I think that you might not be clear at this point of time because there is a lot of concepts to understand in PCA. Let me open another paintbrush. Okay. Now let me take a small example. I will take it as x1 and let's take it variable 1 and variable 2, v1 and v2. Let's say I have the data like the previous example 11, 10, 11, 8, 3, 2, 1, 6, 4, 5, 3, 2.8, 1. Okay, these are my sample 1, sample 2, sample 3, sample 4, sample 5 and sample 6, right? Now we have two variables. It's very easy to visualize, right? Because it's 2 variables, right? Now let's try to take this particular problem statement and convert this particular data into 2 principal components. Now some of you might be asking that it's already having 2 variables. Now if we are converting into 2 principal components, how does it make sense? How does it help us? Now to make you understand how principal components are created, the only example I can take is by taking 2 variables. Only when you understand how 2 PC components are created from 2 variables, then you can imagine how the algorithm works in behind. Okay, when you have 100 variables, definitely I cannot take an example of 100 variables and show you as an example, right? Because I cannot visualize it and I cannot show you properly. So that is the reason I'm just taking 2 variables. But our main concept is if we have n variables, we have to convert it into n principal components. And once we have n principal components, we can prioritize and take the top 3, top 5, top 10, top 15, whatever, like as per our needs. Okay. So let's try to plot this graph. I'm just taking a graph. So let's say I'm just plotting 1, 2, 3 till 10, 11, something like that. So let's try to plot the graph. 10 and 6 somewhere around here, 11 and 4 somewhere around here, 8 and 5 somewhere around here, 3 and 3 somewhere around here. Sorry, let me just redo it. Somewhere around here, somewhere around here, and somewhere around here. Okay, so this is how my data looks like. Now quite clear, this is my variable 1 and this is my variable 2, right? Now what we need to do is we need to calculate the average measurement of variable 1 and variable 2. Now how to measure that? Obviously quite simple. If we add it and divided it, so we are taking the mean of V1 and mean of V2. So what is the mean of V1? 10 plus 11, 21, 29, 32, 34, 35. 35 divided by 6, somewhere around 6. Okay. And here, what is the mean? 6 plus 4, 10, 15, 18, 18, 3, 21, 22. 22 by 6, somewhere around 3.8. Okay. So this is going to be our centroid. Okay, somewhere around here. Clear? This is going to be our centroid. Okay. Now, our very next step will be, let's try to go to the next slide, or you can say the next paintbrush, and try to see. So I hope you are clear with this particular graph. Let me go to a different graph. Here we will try to understand. Let me draw a line. Okay. And let's say I had points like somewhere around here. Sorry. Here, then here, then here, then here, then here, and then here. Somewhere here, right? And this was my centroid location. So our next step, the first step is clear. The first step is calculating the average measurement of V1 and V2. Okay, this is my V1 and this is my V2. Our next step will be calculate the center of the data, which we have calculated, right? This is the center of the data, the red cross. Now, what we need to do is we need to convert the center as the new centroid. That means here our centroid is here, right? 0, 0. Now what we need to do is we have to create a new graph. Just imagine this graph. So the new graph should look like this. So the new center, which is 6, 3.8, somewhere around that. I'm not completely sure about the points, exact points, but yeah, just assume it's 6.6 and 3.8. So our new centroid will be converted into this. So centroid, which is at 0, should be converted into 6, 3.8. Let's try to draw this again. Okay. Let me draw the points. So let's say somewhere around 1, 2, and 3. Let me draw this as a circle. And let's say 1, 2, and 3. Okay. We are not much concerned about the exact points, but yeah, this is how it should look like. So we have shifted the data to the center, as a new origin. So the new origin is nothing but 6, 3.8. Now you can see, you might be thinking, what is the benefits of this? Now there will definitely be benefits. I'll talk about that, because we are migrating from n variable to n PC components, right? So that's the reason we are performing this step. Now you can see that the features importance are not changing. In the first graph, this particular point was still the rightmost point. In the new graph also, it is still the rightmost point. In the old graph, this point was still the leftmost point. In the new graph also, it is still the leftmost point. This point was the highest point. This is still the highest point. So the features are not changing. The importance of any feature is not changing. The characteristics of the variables are not changing. Okay, that's the main idea. Now, what we need to do is we need to fit a line across these points so that the distance between each point to that particular line should be the lowest. let me redo this. This is our latest graph, and let's say point 1, point 2, and point 3, point 4, point 5, and point 6, something like that. Okay, so what we need to do is, next step is going to be fitting a line. Now what is fitting of a line? Fitting of line we have to do so that the line should cross to this particular center, okay, and it should have the minimum distance from each point. Now definitely it can be any line, right? Let's say we start with this line. Just assume it's crossing through the center. Let's say the second line is here. Okay, and there will be millions of lines, right? Millions of lines which can be created. Now definitely the best line should be based on a Euclidean distance concept. Now what is that? So we have to calculate the distance. Let's say this is line number 1, L1, this is L2, and let's say hypothetically I'm talking about this particular line, which as per me should be the best line. Okay, line 3. Now obviously how to find that? How to find whether L1, L2 or L3, which is the best line? We can do this. We can let's say for L2 we can calculate the Euclidean distance from this point to this point, from this point to this point, from this point to this point, from this to this, from this to this, from this to this. Okay, now the value will be definitely higher, right, as compared to L3. So this is how we have to finalize a line which is going to be the best fit line. Okay, let's assume we have converted, and let's say L3 is going to be the best fit line. Okay, now what's our next step? Our next step is going to be rotate this line. So we understood, right? We have to rotate this line until it fits the data, right? So and our prerequisite was that this line should always cross to the centroid, the center location, which is nothing but 6,3.8. Okay, so now what else? Okay, now what we will do is we will just tilt this graph so that our L3 is our new x-axis. I will try to create a new paintbrush or a new window. So in the previous graph, you can see this graph looks like this. We have the points. So our best fit line was L3, right? L3 is the best fit line. So what we will do is we will just shift this graph and make L3 as the x-axis. Let's do it. Okay, I'm calling it as L3, but yeah, obviously we cannot call it as L3. Let's consider this as x-axis and y-axis. Okay, but yeah, ultimately this is our L3 as per this example. Now you can see how the points are. 3 points are beneath this line. Let's say here. Okay, and let's say few points are above this line. Let's say here. Okay, just assuming that. Okay, so L3 is my new point, or else this point is down, right? You can see this point is below the line and these 2 points are above the line. Okay, so let's say this is our new graph. Now I hope you are clear with this point. This is our new graph where our new x-axis is nothing but the best fit line. Best fit line is converted to the x-axis. Here, this is your final graph, and this you can call it as, instead of x, you can also call it as PC1, and you can call it as PC2. So this is your principal component 1, and this is your principal component 2. Now let's try to understand what should be the recipe, how much components of PC1 and how much value, like what should be the ratio of PC1 is to PC2, what is the importance of each component right now, with just a small illustration. Just consider this point, let's say this point. Okay, now what we will do is we will try to find this value, like how far is this point from the x-axis or from the PC1 axis. Let me draw a triangle here. So I'm just enlarging this triangle here. let's say this is O, this is A, and this is B. Okay, O, A, and B. Now this is your right angle triangle, right? OAB. Now, for example, I don't know the exact value. What is going to be the value of OB? Not pretty sure. So just assume. Let's say in x-axis it is having 4, and in y-axis it's having 1. Okay. So that means this point, considering PC1 as my x-axis, the value of this point is nothing but 4, 1. Okay. Okay. Just an assumption, but yeah, the real values would be somewhere around, I think 3 dot something, and this will be 1 dot something. I don't know, but yeah. So let's consider OB is 4 and AB is 1. So what is going to be the value of OA? Now from this, it's quite clear that to make PC1, the recipe is 4 parts of variable 1 and 1 part of variable 2. This makes my recipe for PC1. Now variable 1 is more important as how the data is spread out. Now this is also called as, you can write it down, it is also called as linear combination of two variables. Linear combination of two variables. Okay. Or it is also called as PC1 is linear combination of variables. It's also almost the same value. It's almost the same meaning. Okay. Now, I'm just talking about this particular triangle. Now, once we have OB and AB, the value of OA is going to be, so we know the Pythagoras theorem, right? OA is going to be OB square plus AB square root over. So what is OB square? 16 plus AB square 1 root over. So 17 root over. We can calculate the value of 17 root over 4.12. Okay, that's going to be 4.12. Okay, now what else? So we have three different values. Let me redraw this again. O, A, and B. Okay, this is 4, this is 1, and this is 4.12. Now if I have to scale it down to 0, between zeros and ones, what we can do is OA can be converted into 4.12. So let me write it down first. AB equals to 1 and OB equals to 4. Now if I want to scale it down to 0, between 0 and 1, what we can do is divide everything by the largest number, right? So 4.12 divided by 4.12, 1 divided by 4.12, it's going to be, 1 divided by 4.12, 0.24. This is going to be 4 divided by 4.12. It's going to be multiplied by 4, 0.97. Okay, so this is my new combination, or you can say new recipe. So here the recipe was 4 parts of variable 1 and 1 part of variable 2. Now to make PC1, the recipe is 0.97 parts of variable 1 and 0.24 parts of variable 2. This is your new recipe. If you look at this particular ratio, V1 is to V1 is to V2 is still 4 is to 1. If you just divide 0.94 divided by 0.24, it is still 4 is to 1. Okay, but the values are scaled down right now. Now this is known as your singular vector, or it is also called as eigenvector for PC1. Singular vector or eigenvector for PC1. Okay, so these proportions are basically called as your loading score. Sometimes being asked in the interviews as well, what is loading score in terms of PCA? You can tell about this thing, like the recipe which is required to create PC1 let's say variable 1 to variable 2 is 4:1, we have to convert it into, scale it down to 0, between zeros and ones, or else we can convert it into a singular value, you can say that. And the recipe required is known as loading score, and the value which we get after converting or scaling down to singular format, or the format between 0 to 1, that's basically called as your singular vectors or eigenvectors for PC1. Now similar concept, let's talk about PC2. Okay, I have the same graph, I'm just redrawing it. So this is PC1 and this is PC2. Okay, now I'm just considering this particular point. So as compared to PC1, so it was 4:1, right? Now if I just draw this graph on PC2, how will it look like? It will look like this, right? Now let's say this is O, this is A, and this is B. So the value here is -1, here is 4, right? Or else if you want to convert it in other ways, like if you want to project PC2 as x-axis and do it, that's also fine. If you want to project PC2 as my x-axis, let's say PC2, so you can see if this is your center, this point is falling towards the left side, right? So this is where the center is falling. Sorry, the value is falling, right? Now if you just do this, it will be 4 parts and -1, right? Similar only. So here it is 4:-1. So the recipe for PC2 is nothing but -1 parts of variable 1 and 4 parts of variable 2 makes the recipe of PC2. Okay. Now what will be the eigenvalues for PC2? For PC2, -1, just convert it into -0.24 of variable 1 and 0.97 of variable 2. This is going to be your eigenvalues. Okay, or you can say the singular vector. Sorry, the eigenvectors, right? This is the eigenvector for PC2. So that's it. That's it for, yeah, I mean, the main concept is clear, right? So we are able to find the PC components. Now, once we get the PC components, so here in this particular example, we took 2 variables and we were able to get 2 PC components. So in real scenarios, what happens is, let's say you have n variables, you might have n PC components, out of which you can select as much as you can. Like if you are able to, let's say I'm just having 150 variables. 150 variables will definitely make 150 PC components. Now, for example, by just using 50 components, you are able to get an accuracy of 90%. Now, why there is a need of adding more, like adding further 100 features and making it more complex, in terms of memory, in terms of complexity, time complexity, space complexity, and all those things, right? So it's all about the developer, or you can call it as the machine learning engineer or the data scientist, to take a call how many components he is going to use in this particular model. I'll just simply give you an example, or I would say from the code point of view. I'll also share this code as part of the description. You can check it out. This was one of the interviews, as part of one of the interviews, I was given this particular problem statement and I was asked to scale it down. Like I was given like more than 150, 170 variables, and I was told that just perform feature selection on this particular use case and shows the results. So I had done using both scenarios. You can see there is a random forest feature selection which I had done. I had also done PCA, but the results with PCA were far better. So that was the reason I provided them, and I was also selected for that particular thing. But yeah, it was way back in 2017. Now the interview processes has changed. They will not directly ask you to do some sort of these kind of problems. They will definitely give you some use cases around classification problems or something like that, end-to-end projects in case they have to. But yeah, let's just talk about this particular use case. So this was nothing but, let me show you the training variables, the training labels. So this is how the data looks like. I have more than 33 variables. That means 33 classes. Okay. And the training data, you can see training data looks like x1 x2 till x145. Now what is x145, what is x144? I don't know, because in some scenarios when you are working on real life projects, you might be working on some data which is not meant to be shared with anyone, might be because of privacy or something, right? So there is a chance that you might have to select, might have to sign some NDAs and all those things. Especially it happens in finance domain or banking domain. You are not allowed to know the personal traits of a customer, right? That is the reason they mask the data to x1 x2 x3 and so on. So maybe that could be one of the reasons why I got this data as x1 x2 till x145. And I was given this problem statement to cut down the variables to as much as I can and still get the required amount of accuracy in prediction. Okay, so what I did is I'll just quickly run through this program. Maybe you can just take a look at it. Uh, and obviously this program is not pretty, like it's just done in couple of hours, and it's not the way we should also code. So I'm apologies if my coding is not that great, because it's like 3 years old program. So let me run it. So here I'm reading the class files, I'm reading the training data and reading the y variable, the target classes. And here I'm doing some hard coding, which is actually not allowed. But yeah, I did some hard coding. And here I'm doing a standard scaling. So I'm just calling my feature scaler, standard scaler. I'm just fitting transform the x value. And here's the main part. Here's the main part. I'm just importing PCA. PCA comes under your sklearn.decomposition library. I'm importing PCA. I'll just quickly run this. And PCA takes two inputs. Okay, you can either pass, like here I'm instantiating my PCA object, right? So you can do this way, or you can also do this way, 0.9. Okay, now there are two techniques. It can be, you can provide n components, or you can provide the accuracy. Let's just talk about the n components as of now, as I have already have 145 components, right? So let's try to see what will be the accuracy if I just use 30 components. Okay, so I'm just running this program, simple program. I'm just calling PC and then just transforming the data, fitting the data, calling the data frame, and just checking the variance and accuracy. That's it. So I'll just run this program, and you can see just by using 30 components, that means from 145 to 30. So we have cut down the number of features to like from 150 to 30, somewhere around 20%. So we are just using 20% of the features that was given to us, and we are still able to get 82% accuracy. Okay, now let's say I'll do it as 60. 95% accuracy. So it's all up to a developer's call. Like how many components do I have to use? It's all about what is your bandwidth, what is your hardware specifications available in your company. If you are okay with like more number of components, then you can make 100 components, and you can compromise on that part. But yeah, if you compromise on that part, your accuracy will go high, but yeah, it will be computationally expensive. So let me show you how it works with the accuracy. Let's say I'm just concerned about 85% accuracy. How many number of PC components I'm getting, I don't care. I just want 85% accuracy. So what I can do is I'll just pass 0.85, and I'll see, okay, by using these much components, I'm able to get accuracy of 85. How many components? 1, 2, 3, 4, 5, 6. 6 into 5, 30, 31, 32, 33, 34. So with 34 components, I'm able to get 85% accuracy. So it's, as I told, it's going to be your call. And yeah, this is just a basic program on PCA. But yeah, at the end of this particular series, once I go through LDA, QD, and Kernel-PCA, I'll also be talking about a real life example where I will show you how to perform PCA, how to perform LDA, how to perform normal random forest based feature selection, or a decision tree based selection, or some other techniques. RFE maybe, and I'll show you how it works in the real scenarios, right? So for the time being, that's it for today's video. That's it for PCA. Okay, just a disclaimer, this is just the part 1 of PCA. The mathematics part is still yet to come. In the next video I shall be releasing about the mathematics part, right? How to solve a PCA problem using maths and statistics, right? So that's it guys, thank you, thanks for watching. Please like and share the video, subscribe to my channel, and keep supporting. Thank you.